Hello बच्चों, this is the lecture number 13 of the unit Electrostatics, and today we are going to start the second chapter in which we will study electrostatic potential energy difference and electrostatic potential energy. Second topic will be electrostatic potential difference and electrostatic potential. Third, electrostatic potential due to a point charge. Fourth, electrostatic potential due to an electric dipole. 5. Equipotential surfaces. And 6. Electrostatic potential energy of electric dipole in a uniform electric field. So first topic is electric potential energy difference and electric potential energy. So firstly we will discuss what is the electric potential energy difference, and from this we will move on to electric potential energy. So the electric potential energy is the energy that is needed to move a charge against the electrostatic force in an electric field, or this energy is similar to the gravitational potential energy which is possessed by a mass in a gravitational field. In the similar way, we can say the potential energy possessed by charges in an electric field is called electric potential energy. For this, we can consider a positive source charge Q kept at a fixed point considered as origin, which is producing an electric field around it. Another positive test charge is brought from point S to P in its electric field against the force of repulsion of the source charge, denoted by Fe, between Q and Q naught, in such a way that the external force which we are applying on the test charge to compensate the electric force of source charge, so that we can move the test charge from point S to point P without acceleration in it. So there must be work done to overcome this repulsion, and this work done is stored in the form of electric potential energy in Q naught. Here, in bringing the charge Q naught from S to P, the work has to be done, and that work is stored in the form of electric potential energy in the test charge Q naught, and therefore the electric potential energy difference between the 2 points S and P in moving the charge from S to P is given by delta U is equal to UP minus US, that is U final position minus U initial position, which is again equal to WSP, which is work done on the charge in bringing it from S to P. And we can write this work done in two forms: in the form of using external force done by external agent, and in the form of electric force exerted by the source. Here it is showing that the work done by the external agent on the test charge is equal to the work done by the source on the test charge. But the negative sign shows that the forces are equal and opposite. Therefore, we can say that in moving a test charge in the field of the source charge from a point to another point, the net force must be 0 on that, so that there will be no acceleration in it. Since Coulomb's force is conservative, so work done is independent of the path, and it depends only on the initial and final position of the test charge. If we choose 0 potential energy at infinity, then we can write, that is, we are considering S point at infinity, and at infinity the energy is 0. Therefore, we can write work done W infinity P is equal to delta U is equal to UP. Since the energy at infinity is 0, so the term U infinity will become 0, and we get the potential energy at point P. From this equation, we can define electric potential energy as electrostatic potential energy of Q naught at a point in an electrostatic field of any charge Q is work done by the external force F external, which is equal and opposite to the electric force Fe, in bringing it from infinity to that point. Second point is electrostatic potential difference and electrostatic potential. In this topic, as we have done before, we will firstly understand what is electrostatic potential difference, and then we will move from that topic to electrostatic potential. So, electrostatic potential difference between 2 points in an electric field is the amount of work needed to move a unit positive test charge without acceleration from one point to another point against the force of electric field. Here we have considered S and P are 2 points in between which we are moving the test charge from point S to point P. Therefore, we can write electrostatic potential difference according to this statement. Delta V is equal to WSP by Q. Again, by choosing the 0 potential at infinity, that is, we can consider the potential at point S from which we are bringing the unit positive test charge is equal to 0. So, we can write the potential at point P in the electric field of the source charge is equal to W P by Q. Therefore, we can define the electrostatic potential from this formula as electrostatic potential at any point in a region of electric field is the amount of work done in bringing a unit positive charge from infinity to that point without acceleration. Our next topic is electrostatic potential due to a point charge. Now we have got the concept of the electrostatic potential and formula also, that is electrostatic potential V is equal to W by Q, that is work done per unit charge. So we will use that formula for this derivation and find out the electrostatic potential due to a point charge. For this, let us consider a point charge plus Q situated at point O, which is a source charge, and it has its own electric field around it, and the magnitude of electric field intensity is given by E. Q naught is a test charge at infinity, and its magnitude is 1. P is a point at which electric field is to be obtained, and in figure OP is equal to R, OS is equal to X, ST is equal to dx, and F is the external force acting on Q naught by an external agent. Here, electric field intensity at point S can be written as E is equal to 1 by 4 pi epsilon naught Q by x square, and the direction will be from O to S. Let a small amount of work dW is done in moving the test charge from point S to point T, and the displacement between these 2 points is dx as shown in figure. Then dW can be written as dW is equal to F dot dx. Here, by using the formula of electrostatic force F is equal to Q into E, we can write F is equal to plus 1, which is the magnitude of the test charge, into electrostatic field dot dx. Now dW become E dot dx, and by opening the dot product we get E dx cos 180 degree, since there is 180 degree angle between electrostatic field and dx as shown in figure, and the value of cos 180 degree is minus 1. Therefore, we get dW is equal to minus E dx. Now, total work done in moving a unit positive test charge from infinity to point P can be obtained by integrating the equation number 2 from the limits infinity to R, and by putting the value of E in the equation we get W is equal to minus integral infinity to R Q by 4 pi epsilon naught x square into dx. Or we can write W is equal to minus Q by 4 pi epsilon naught integral infinity to R 1 by x square dx. Here Q by 4 pi epsilon naught are out of integration because it is a constant value. By integrating 1 by x square with respect to x and putting the limits, we get W is equal to Q by 4 pi epsilon naught 1 by R minus 1 by infinity. As we know that 1 by infinity is equal to 0, therefore we get the work done is equal to Q by 4 pi epsilon naught into R. Now by definition we can say this work done will be equal to the electrostatic potential at point P due to Q, and hence V is equal to Q by 4 pi epsilon naught into R. This is the required expression. Next topic is electrostatic potential due to an electric dipole. For this, let us consider an electric dipole AB of length 2a having center at O and charge of Q magnitude on each pole. P is the point of observation at which we have to find out the electrostatic potential at an angle theta from the electric dipole, that is the angle BOP is equal to theta, and the distance of P from O is R. The distance PB is equal to X and PA is equal to Y. Now, as we know the expression of electrostatic potential, we can write V at P due to plus Q charge of the dipole as V1 is equal to Q by 4 pi epsilon naught X, and electrostatic potential at P due to minus Q charge is V2 is equal to minus q upon 4 pi epsilon naught into y. Now according to principle of superposition, the electric potential at P due to the dipole is given by V is equal to V1 plus V2. By putting the value of V1 and V2, we get V is equal to Q by 4 pi epsilon naught 1 by x minus 1 by y, which is equation number 1. See in the figure, if we extend the line PO beyond O as shown in figure and draw a perpendicular from point B and point A, which is BM and AN respectively. Now, if P point is too far from the electric dipole, then we can say that the distance PB is equal to PM approximately, and similarly PA is equal to PN. Therefore, we can write PB is equal to PM, and from figure this length PM can be rewritten as OP minus OM. By putting the value of PB and OP, we get x is equal to R minus OM. Similarly, we can write y is equal to R plus ON. We can obtain these values OM and ON from figure and by using trigonometry as solved in the next slide. To obtain the value of OM and ON, we can see in the triangle OBM, cos theta is equal to OM by OB, and from here OM is equal to OB cos theta, and we can see that OB is equal to A since O is the center of the dipole, so OM is equal to A cos theta. Similarly, ON is also equal to A cos theta. Now putting these values in the last two equations, we get x is equal to r minus a cos theta and y is equal to r plus a cos theta. Now putting the value of x and y in equation number 1, we get v is equal to q by 4 pi epsilon naught 1 by r minus a cos theta minus 1 by r plus a cos theta. Now by solving and rearranging the equation, we get v is equal to 1 by 4 pi epsilon naught q into 2a cos theta upon r square minus a square cos square theta. As we know that the electric dipole moment P is equal to q into 2a, so we can put the value in the equation as v is equal to 1 by 4 pi epsilon naught p cos theta upon r square minus a square cos square theta. As we have considered that if point P is too far from the dipole, in that case r will be much greater than a, and in that case we can neglect a square cos square theta in the denominator. So we get the final expression of electrostatic potential due to an electric dipole at a point P. V is equal to 1 by 4 pi epsilon naught P cos theta upon R square. Next topic is equipotential surfaces. Here the meaning of this topic is hidden in its name, as it is composed of two words which are equal and potential, and combining these two it becomes equipotential. So the meaning of equipotential surfaces are the surface at which the potential at each point is equal. Therefore, we can define equipotential surfaces as it is the surface at each point of which electrostatic potential is same, or in other words, the surface which is the locus of all the points which are at the same potential is known as the equipotential surface. There are some properties of equipotential surface. First is the work done in moving a point charge from a point to another point on an equipotential surface is equal to 0. As we can write the expression W is equal to Q naught VA minus VB. Here we are moving the charge Q naught from point B to point A, and according to definition, the potential at both the points B and A are same, so that the work done will be equal to 0. The next property is the electric field is always perpendicular to an equipotential surface. We can prove this also as W is equal to E dot dA or E dA cos theta. Here in this equation, as we know that E is not equal to 0, also dA is not equal to 0, therefore cos theta is equal to 0, and cos theta has value 0 for theta is equal to 90 degree, which proves the statement. Next property is two equipotential surfaces can never intersect. This is because two different equipotential surfaces have different electric potential. So if they intersect, then at the point of intersection there will have two different potentials, which is not possible. Next property is the direction of equipotential surface is from high potential to low potential. For a point charge, the equipotential surfaces are concentric spherical shells as shown in figure. First figure shows the equipotential surface in a uniform electric field. The surfaces are parallel to each other and perpendicular to the direction of electric field. That is, the area vector of the equipotential surface and electric field are in same direction. And second figure shows the equipotential surfaces due to a point charge, and in this case the equipotential surfaces will be concentric spherical shells. And last figure shows the equipotential surfaces due to an electric dipole. Our last topic is electrostatic potential energy of electric dipole in a uniform electric field. To obtain the expression of electrostatic potential energy, let us consider an electric dipole AB having Q charge on each pole. O is the center of the dipole and the length of the dipole is 2a. Dipole is subtended at angle theta from the electric field E. P is the electric dipole moment of the dipole and E is the electric field intensity. As we know that in a uniform electric field, an electric dipole experiences a torque which is given by P cross E or PE sin theta n cap. Here n cap is showing the direction of torque which will be perpendicular to both electric dipole moment and electric field intensity. Now this torque rotates the dipole unless it is placed parallel or anti-parallel to the electric field. If we apply an external and opposite torque, tau external, it neutralizes the effect of torque due to electric field and let it rotate the dipole from the angle theta 1 to an angle theta 2 at an infinitesimal small angular speed without any angular acceleration. So the amount of work done W by the external torque can be given by tau is equal to integral theta 1 to theta 2 tau external d theta. Here d theta is infinitesimally small angular displacement. And by putting the value of tau external, we get W is equal to integral theta 1 to theta 2 Pe sin theta d theta. Since P and E are constant, therefore it will be out of integration. So by integrating sin theta from the limits theta 1 to theta 2, we get W is equal to Pe minus cos theta from lower limit theta 1 to upper limit theta 2. By putting the limits of theta, we get W is equal to Pe minus cos theta 2 plus cos theta 1. Rearranging this equation, we get W is equal to Pe cos theta 1 minus cos theta 2. This work done will be stored as a potential energy in the dipole. Therefore, we can write electric potential energy of a dipole in a uniform electric field U is equal to Pe cos theta 1 minus cos theta 2. Today you have a lot of homework. First one is find out the electrostatic potential at a point due to system of charges. You have done the similar problem in previous lectures for force and electrostatic field. In this you have to use the superposition principle and write down the expression for electrostatic potential. Second is prove the electrostatic forces are conservative. Third, derive a relation between electric field intensity and electrostatic potential. And the relation is E is equal to minus dV by dr, which is also known as potential gradient. Second last is derive an expression for electrostatic potential energy of a system of 2-point charges. And the last is study the cases of electric potential energy of an electric dipole, which we have done lately. Thank you.